A black hole smaller than a speck of dust accidentally enters a person's body. Then, like a ghostly bullet, he's shot straight through the Earth's core from head to toe. At this moment, people are terrified to discover that no one can stop him. This is a scene from the 1975 Hugo Award-winning short story, The Hole Man. However, in reality, physicists have seriously studied this question. What happens when a miniature black hole enters your body? Will you die instantly or not notice anything at all? Science suggests the outcome might not be so straightforward. We often imagine black holes as gigantic entities. Whether it's a stellar mass black hole formed from the collapse of a star or a supermassive black hole at the center of a galaxy, both their mass and size are on an astronomical scale. However, scientists propose that there might be another type of black hole in our universe, originating from the dawn of the universe, known as primordial black holes. In the early universe, space was extremely crowded due to limited expansion. During this time, density fluctuations could cause certain regions to have higher material density than others. This density difference might lead to the direct collapse of matter in high-density regions into black holes. These primordial black holes, formed from the direct collapse of primordial matter, vary greatly in size. Some can be as massive as millions of times the sun's mass, while others can be so small that they evaporate instantly due to Hawking radiation. Fortunately, the intensity of Hawking radiation is inversely related to the mass of the black hole. The larger the black hole, the weaker the Hawking radiation, and the longer its lifespan. For instance, a small black hole weighing 1,000 tons has a lifespan of about 1 minute. However, a 1,000,000-ton black hole can last 1,000 years. When the mass reaches 1 billion tons, the black hole's lifespan can exceed the age of the universe. Therefore, scientists believe that although most primordial black holes have evaporated in today's universe, those with a mass over 1 billion tons could still exist. If such primordial black holes do exist, there might be many floating in today's universe, and even a small portion of dark matter's mass could be attributed to these primordial black holes. This raises the question, if such small black holes exist in reality, what would happen if we accidentally collided with one someday? Most people's instinct would probably be, we're doomed. After all, black holes can trap even light. If one were to enter our body, wouldn't it instantly drain us? This intuition actually arises from common misconceptions about black holes. The scenes we often see of black holes devouring stars can only be achieved by black holes that are at least stellar-sized. For tiny miniature black holes, their ability to swallow matter is extremely limited. How small are these miniature black holes really? A distant black hole weighing 100 billion tons is roughly equivalent to a giant mountain. Its Schwarzschild radius is just 0.15 picometers, smaller than an atom and about the size of an atomic nucleus. If something this small were to pass through your body, it would most likely not even touch your tissues, including the molecules and atoms that make them up. Forget about causing any harm, you probably wouldn't even notice it. In fact, when it comes to miniature black holes, their destructive power doesn't stem from kinetic impacts like a bullet, but rather from two other gravitational effects. The first aspect to consider is the tidal force effect. Tidal force is not the same as gravity. It refers to the difference in gravitational pull experienced by various parts of an object within a non-uniform gravitational field. More concentrated gravitational source, greater tidal force. Black holes have extremely concentrated gravitational fields, which means that cells along their path can experience intense stretching. If the force is sufficiently strong, it can even tear some cells apart. Scientists have calculated that this phenomenon might occur when a black hole's mass reaches 10 trillion tons. 10 trillion tons may sound like a lot, but a black hole of this size is still smaller than an atom. However, tidal force is not the most dangerous factor. In comparison, the shockwave effect caused by gravity poses a greater risk. It's important to note that the shockwave mentioned here isn't the traditional kinetic shockwave, but rather a gravitational disturbance that doesn't require a medium. When a black hole moves through the body at the typical speed of dark matter, approximately 200 kilometers per second, it generates a powerful gravitational disturbance along its path. This disturbance creates a small yet highly energetic shockwave akin to a supersonic bullet, which tears apart the tissues surrounding its path. Calculations indicate that unless a black hole's mass is less than 100 billion tons, it would pierce through your body like a bullet, causing severe damage. The crucial point is that such a black hole is only the size of an atomic nucleus, and it might actually exist in the universe today. Sai, are you starting to feel a little shaken after hearing all this? Don't worry, how likely is it for such an event to actually happen? Scientists have calculated that even if primordial black holes accounted for all the mass of dark matter, their density in the universe would still be incredibly low. Assuming a boundary of 100 billion tons, the probability of a black hole colliding with a human body among the world's 8 billion people each year is only 1 in 10 billion billion. In other words, it would occur once every 10 billion billion years. This time span is over 70 million times the current age of the universe. Instead of worrying about being hit by a black hole, you should be more concerned about being struck by a meteorite. However, the above scenario assumes a black hole is rapidly passing through the human body. What if a black hole moves very slowly, or even lingers inside the body as it passes through? First, it's highly unlikely for a celestial body to approach Earth at an extremely low speed. Let's assume this black hole initially moves very slowly, but as it gets closer to Earth, the gravitational pull increases, causing its speed to increase as well. It's similar to a stone in free fall. No matter how small its initial speed, gravitational acceleration ensures that its speed won't be low when it reaches the ground. Additionally, meteorites experience atmospheric friction that slows them down, whereas black holes have almost no means of deceleration. Secondly, even if for some reason this black hole were quietly placed inside our body, it would still be unlikely to remain there. This is because, apart from gravity, there is almost no interaction between this black hole and matter. To it, our body, including the Earth, is like air. Once it enters the human body, it will naturally fall in freefall due to Earth's gravity. The entire process is akin to moving through an uninhabited space, continuously passing through various materials: the human body, shoe soles, floors, ground, rocks, all the way to the Earth's core. And then, it would most likely continue to fall, passing through the Earth's core. However, under the influence of Earth's gravitational pull, it might eventually oscillate back and forth near the core. Imagine if, for some reason, a black hole were to stop at the Earth's core. Would it eventually swallow the entire planet? Scientists have also calculated this question. If a micro-black hole were to enter the interior of a planet or asteroid, it could indeed slowly consume the core, leaving behind a hollow shell. But the problem is, this would take an incredibly long time. To consume something, you first need to be able to reach it. Given the atomic scale size of a micro-black hole, its accretion cross-section is extremely small, meaning it might only consume a few grams of material each year. Therefore, for a micro-black hole located at the Earth's core to grow to the mass of the Moon, assuming its accretion efficiency remains constant, the time required would far exceed the age of the universe. Before it could devour the Earth, the Sun, as it transforms into a red giant, would likely swallow the Earth first. In summary, the risk that micro-black holes pose to Earth, or individual humans, is almost negligible. So, what is the significance of this research? The significance lies in the possibility that if primordial black holes truly exist, we can identify them by the microtunnels they leave when passing through solid matter. Although this method is challenging, it is much more cost-effective to examine ancient rocks and meteorites compared to using large scientific devices like particle colliders. It might even offer crucial clues to unraveling the mystery of dark matter.